Hello everyone and welcome back to the channel. Today we're solving Heap Havoc, a binary exploitation challenge from picoCTF. This challenge is a great introduction to heap overflows because it demonstrates how an unsafe memory operation can be used to overwrite a function pointer and redirect the program's execution. Our objective isn't to inject shellcode or bypass modern protections. Instead, we'll understand the vulnerability, analyze the binary, identify the target function, and gather all the information needed for exploitation. Let's get started. The first thing I like to do whenever I receive a binary is inspect it before opening the source code. We'll begin with the file command. This tells us what type of executable we're dealing with. From the output, we can see that this is a 32-bit ELF executable. It is dynamically linked, which means it relies on shared libraries at runtime. More importantly, the binary is not stripped. Since the symbols haven't been removed, functions such as main and winner are still visible, making our analysis much easier. Next, let's inspect the binary's security protections using checksec. Several important protections are listed here. First, notice that NX, or non-executable memory, is enabled. This prevents injected shellcode from executing in writable memory regions such as the stack or heap. However, that doesn't stop us from reusing code that's already inside the binary. Another important protection is PIE, or Position Independent Executable. In this challenge, PIE is disabled. That means the binary is loaded at the same memory addresses every time it runs. Because the addresses remain constant, any function address we discover during analysis can later be used reliably without leaking memory addresses first. With the reconnaissance complete, let's examine the source code. The program defines a structure named internet. This structure contains three members. The first member is an integer called priority. The second member is a pointer named name, which points to dynamically allocated memory where user input will be stored. Finally, the structure contains a callback function pointer. Unlike ordinary pointers that reference data, a function pointer stores the address of executable code. If the program later calls this pointer, execution jumps directly to whatever address it contains. Initially, both callback pointers are set to null, meaning they don't point to any function. Next, the program allocates memory on the heap. It first allocates memory for the structure itself. Then it allocates another block of only 8 bytes for the name field. The exact same process is repeated for the second structure. At this point, everything appears perfectly normal. Each structure has its own heap allocation, and each name buffer has enough space for only a small amount of input. Now we arrive at the most important part of the program. The user input is copied using the strcpy function. This function has one major weakness. It performs no bounds checking. Instead of verifying the size of the destination buffer, it simply continues copying characters until it reaches the null terminator. Remember that our destination buffer is only 8 bytes long. If the user provides more than 8 bytes of input, strcpy doesn't stop. Instead, it continues writing past the end of the allocated buffer. This is the heap overflow vulnerability. Rather than remaining inside the intended allocation, the write operation begins corrupting neighboring heap memory. Why is that dangerous? Because immediately after the first allocation, the program creates another structure. If the overflow is large enough, it doesn't just overwrite random data. It begins modifying important members inside the second structure. That includes the priority field, the name pointer, and eventually the callback function pointer. A corrupted integer might simply change a value. A corrupted pointer, however, changes where the program reads or writes memory. A corrupted function pointer is even more powerful because it determines which function the CPU executes next. Near the end of the program, we find two simple conditional statements. The program checks whether each callback pointer is not null. If the pointer contains a valid address, the program immediately calls it. Under normal circumstances, nothing happens because both callback pointers were initialized to null. But imagine what would happen if an attacker replaced that null value with the address of another function already inside the program. Instead of doing nothing, the program would jump directly to that function and execute it. That is exactly what makes this vulnerability so dangerous. Now we need to identify a useful function already present inside the binary. Because the binary is not stripped, and because PIE is disabled, locating function addresses is straightforward. Using objdump, we search for the function named winner. The output shows that winner begins at the address 0x080492B6. This address becomes our target because it never changes while the binary remains compiled without PIE. To verify our findings, we can inspect the function itself. Inside winner, the program opens the file named flag.txt. It then reads the contents of that file into a buffer. Finally, it prints the contents to the screen. This confirms that winner is exactly the function we want the program to execute. Next, we need a safe writable memory location. For that, we examine the program sections using readelf. One of those sections is called .bss. The .bss section stores uninitialized global variables and is readable throughout the lifetime of the program. The section begins at the address 0x0804C040. This gives us a reliable writable memory location that we can safely reference later without causing the program to crash. Finally, let's understand one of the most important numbers in this challenge. The overwrite reaches the callback pointer after 16 bytes. This number isn't arbitrary. It comes directly from the heap layout. The first 8 bytes completely fill the I1 arrow name buffer. The next 4 bytes overwrite the priority field inside the second structure. The following 4 bytes overwrite the name pointer. After those 16 bytes, the next field in memory is the callback function pointer. That is the field that controls where the program transfers execution. Once we understand this memory layout, the entire exploit becomes much easier to follow because every byte of the overwrite now has a clear purpose. At this stage, our reconnaissance is complete. We've inspected the binary. We've analyzed its security protections. We've understood the heap layout. We've identified the unsafe use of strcpy. We've located the hidden winner function. We've found a safe writable address inside the .bss section. And finally, we've determined exactly how many bytes are needed to reach the callback pointer. With all of this information gathered, we now have everything required to build the exploit. In the next part, we'll use these findings to craft the payload and redirect execution to the winner function. Thank you for watching, and I'll see you in the next part.